held high-level executive positions both at SAP and prior to that in Apple. What really caught my attention is that he was one of the guilty parties for Mach, which is still running inside of all Apple devices. So that's a huge impact that he has made. In this session, which is the 13th session of Industry Spotlight, which is sponsored by Corporate Liaison Program of Santa Clara Valley Section and Computer Society chapter of Santa Clara Valley Section, as well as by Industry Engagement Committee of IEEE. Ike will present the talk titled Using a Scaled Up Software-Defined Server as an Alternative to Scaling Out. Ike also denied to admit any accordion playing in his youth. However, he proudly announced that he was city champ of New York rifle team. He also declared that he would prefer to take all the questions at the very end until they are extremely controversial, in which case he'll take them immediately. So you can type your questions in the chat. Well, with no further ado, Ike Nassi.
Thank you, Dejan. Really appreciate the opportunity to do a deep dive into TidalScale technology. It's something I'm pretty proud of. And as you said, there is a question about should we scale it out or should we scale it up? And we'll go into a lot of detail on the technology. So with that, I'm just going to jump right in. So the first question is, what is it? So TidalScale conceived of and defined the term software-defined server. And I credit our CEO, Gary Smerdon, with that term. I really like it. You know, we've talked in the industry about software-defined servers, software-defined networks, software-defined storage. So the missing piece seemed to be software-defined servers. So what it is a distributed virtual machine architecture, and it's distributed over a set of servers. It aggregates all the processors, all the memory, all the disks, all the local storage, all the NICs, and treats the set of resources as a virtual machine. The virtual machine runs across a cluster of closely cooperating, dedicated, but off-the-shelf commodity servers connected by standard Ethernet. And the virtual machine boots a standard operating system. Several are supported. And then the operating system just runs as if it were a single, runs as a single very, very large server. The interesting thing is there's no changes to the OS or any applications that run on that OS. No changes whatsoever. It's 100% bit for bit compatible. So I'd like to go back in time a little bit and discuss some of the historical triggers that caused me to start the company. One was this emerging need for big data. And, you know, big data, in my opinion, required a lot of memory because memory was the right way to do big data. In-memory databases, I was introduced to at SAP. Hasso Plattner, the founder of SAP, had this idea, and I didn't always agree with everything Hasso would say, but this I really agreed with. So in-memory databases for rapid decision support seemed like a very good idea in 2009, 2010. There was a lot of new emerging hardware support starting about 2005 with support for virtualization with Intel's ESX extensions. Of course, the cloud was cranking up around that time. But, you know, to use the cloud, you required complex distributed computing. That was becoming popular, but, you know, distributed computing is hard. And I thought there was a better way to do it. As I said, software-defined networks and software-defined storage seemed like a solved problem. Machine learning was beginning to emerge, and I thought that had a lot of potential, a lot of legs. Density of cores was increasing, but memory was not increasing at the same rate. So the ratio between memory and cores was actually going down, not up. So our goal was to scale up or scale down as needed in a dynamic way. I wanted to make, the lesson I learned at Apple was things should really be easy to use. I wanted to minimize the development time for our customers. Again, no changes to the apps or operating system. And if there's no changes at all, it can't be any simpler than that. We wanted to automatically and dynamically optimize systems. And we'll talk about some of the limits of human intuition a little later in the talk, but I wanted to make better use of machine learning and introspection. And I wanted things to evolve without requiring special hardware. But I wanted to be able to use new hardware when it arrives, but I didn't want to have to count on it. Now, this is the traditional view of virtualization. You have a number of virtual machines and they share a physical machine. That is not what we do. Absolutely not what we do. We flip the whole model upside down. We have a bunch of physical machines and a single virtual machine that spans those physical machines. And that is what we do. Okay, with me? This is my favorite slide out of the Hennessy-Patterson book. Shows the progression of processor cores increasing over time. It shows very clearly that memory is not keeping up with processor cores. And I won't even go into, at this point in the talk, memory bandwidth and IO bandwidth, but there's lots to be said about that as well. The reason why things haven't kept up on the memory side is a picture of a processor. The processors are approaching 3,000 pins. The pins are used for addressing memory, reading memory, writing memory, and so forth. And it's getting to the point where you can't put more pins on these chips. And so you have to find another way to increase the amount of memory in these servers. Fortunately, there's a very smart guy, Peter Denning. Over 50 years ago, he defined the term working set, 1968, communications at the ACM. And he started using that on uniprocessors, which was a really good idea. And he had some analytics to back that up. You can read the paper. It's a good paper. Today, locality is applied ubiquitously across our computing infrastructure. And we at TidalScale apply this locality to all resource types automatically and dynamically across these physical machines. We think in terms of memory hierarchies always. And just to give you a preview of what I'm going to talk about, we think of physical DRAM actually as an L4 cache of the virtual machine. In fact, that's why we call it a cache-only architecture. So if we want to rethink DRAM from a software point of view, here's a picture of 4 servers. The 4 servers have, although we're only showing one CPU, there's multiple CPUs there and multiple banks of memory. Each of those is running in a physical machine. There's a hyperkernel that the physical machine boots into. And these servers at the bottom plane now is connected with a standard Ethernet. The plane above it, the upper plane, has virtual processors and virtual memory and is running a standard operating system like Linux. And there's applications that are running on that as well. So for terminology purposes, we call the bottom plane the host, and we call the top plane the guest. Now, where's the DRAM? Answer, it depends on your point of view. From the host point of view, that is the hardware, it's on the physical motherboard. But from the guest point of view, that is the OS, it's also on a motherboard, but that motherboard is a virtual motherboard. And it could be as large as you want, pretty much. So from the guest point of view, physical DRAM is actually a cache of host memory. It's important to keep that in mind. In other words, guest DRAM is a cache, it's an all-cache design. So what are the implications? Intel and other processor vendors give us multiple levels of cache organized in a hierarchy, L1, L2, L3. TidalScale introduces L4. All the memory on the motherboard, on a standard physical motherboard, is treated like any other cache, except for one thing. The L4 cache is all the memory on the motherboard, on each of the motherboards, and is therefore huge, generally 0.5 terabyte, 1 terabyte, 2 terabytes, or more. From a software point of view, each cache level must treat memory the same way. This is really important. All references to memory must preserve Intel's store order and must have strong cache coherency semantics. And under these ground rules, nothing prevents additional levels of in the cache hierarchy. Page mapping, I want to spend a minute on that. Page mapping is handled by 2 levels of dynamic address translation in modern microprocessors. So When you write a program, say under Linux, you generate these virtual addresses. These virtual addresses are handed off to the processor, and the processor converts it to what it thinks of as a physical address by using page tables. And these page tables, the input on this thing is a virtual address, the output is a physical address. Only today, with modern microprocessors, is actually a second level of dynamic address translation. So that physical address, at least what the OS thinks of as a physical address, we'll call a guest physical address, and that goes through a second level of dynamic address translation, resulting in a real physical address. Okay, with me? A little confusing, but that's the way it is. So what happens under the hood? So again, we will revisit these multiple physical servers. There's each server has is running a hyperkernel instance and has multiple CPUs and multiple banks of memory, multiple I/O channels, and so forth. You know, when they boot up the hyperkernel, boot into the hyperkernel does an inventory of all the resources on those physical systems, and in the aggregate creates this virtual machine, a software-defined server. Now, when there is a virtual CPU, the virtual CPU is actually bound to a physical CPU. That's how it does its work. And it may make a reference to some memory that may or may not be local. If it's not local memory, if it's on a different physical server, then the hardware doesn't know how to get to it. And so there's a problem. And the way that works is, you know, the OS has allowed you to translate to the first level of page table, but there's no definition in the second level page table in that case if it's not there. And so an interrupt is generated, a fault is generated, we call it a stall. And, you know, the hyperkernel is invoked to handle that interrupt. And then what you have to do is figure out how you're going to deal with that. Okay, one simple thing to do is to make a copy or move that memory onto the server that has the virtual processor bound to a physical processor that made the reference in the first place. That's one strategy. However, there's another strategy. That same virtual processor may access that non-local memory, but in this case, another possibility is you might want to move the processor to where the memory is. Okay, now you might think that's an expensive operation. Hold that thought, it's not an expensive operation at all. So we use two levels of dynamic address translation. We migrate virtual processors and virtual memory completely transparently to the guest operating system. It dynamically and automatically load balances. We're using machine learning here and it's self-optimizing. And guess what? There's no central control. So how do we do that? How can this possibly be done? You know, programmers have thought, you know, they want to build these software universes and control every bit in the software universe. David Galerter actually wrote a book about this called Mirror Worlds, but I'm not going to go there. So how do we do this? So let's talk a little bit about nodes, memory, and processors. The virtual machine, as I said, aggregates all the processors, all the memory, all the storage, all the Ethernets, except for one Ethernet, which is the private interconnect that we treat more as a systems bus than a network. It's not visible to the guest operating system at all. All the resources are virtual and mobile. The hyperkernel binds the virtual resources to physical resources on demand. No master node, no shared state in the hyperkernel. Scheduling is completely distributed. Therefore, there's no single point of failure. We use the hardware virtualization extensions provided by the processors. The OS uses the first level. We manage the second level. And processor migration is fast. So you can take a snapshot of the state of a physical processor. It's about 6,400 bytes, and you can move it. Moving 6,400 bytes on a 10 gig Ethernet is pretty damn quick. So no problem there. One instruction to snapshot the state, one instruction to restore the state, and the transmission is, as I said, very fast. Memory is strongly cache coherent. There can be multiple copies of read-only pages across the cluster. Once you write into a page, we do all the necessary invalidation, the TLB management, copy on write is supported. And as I said, Intel store order is preserved. How do I know? Because the OS wouldn't work without it. We sit beneath the operating system and above the hardware. So I don't know anybody else who's running machine learning below the level of an operating system, but that's what we do. We look like hardware as far as the OS is concerned. We do not at TidalScale, we do not want to know which OS is running, or in fact, which applications are running. So when you're writing some of these large programs, you have a choice. You can either scale it up or scale it out. So scaling up is a very convenient thing to do because you just buy a larger computer. All your software continues to run. The downside is it can be very expensive. So supercomputers and very large systems are expensive. So you might think, well, I should scale it out. Well, when you scale it out, your hardware cost is pretty good, but you've lost the software simplicity. Now you're into distributed systems, and there's a lot of complexity around that, unless you go with TidalScale, in which case you get the best of both worlds. So that's my little plug, best of both worlds for TidalScale. You get the software simplicity, and you get the hardware economics that are desirable. And if you do it right, everything just runs. Now, this is not a complete list, mostly because we don't know anything that doesn't run. So as long as you maintain a set of constraints and invariants, and you handle things as if a server would handle them, everything should run, and guess what? It does. We'll come back to that later. Now, what is the migration and decision overhead? I already mentioned some of that. So here we have a number, 5 hardware servers. There's a hyperkernel instance running on each one. Taken together, they boot up an operating system, perhaps a database, and they run a bunch of applications. So where does the overhead come in? Well, overhead is simply the number of stalls times the average time per stall. That's all it is. So you want to minimize, well, through clever coding, time per stall. You can, optimize your code in the hyperkernel to do that. It's really the number of stalls that you want to minimize. You minimize the number of stalls, you're doing well. So here's my philosophical machine learning assumptions. Machines operate much faster than humans. So let's let them do that. Oh, I see Len Kleinrock there. Hi, Len. Performance is dominated by the largely unpredictable pattern of access between processors and memory. I'd love to say we can, design this system for a specific application, but then the data is going to change. Or, and you can't predict when some crazy is going to fly an airplane into a skyscraper, or there's going to be a tsunami disrupting a supply chain in Thailand, and just can't predict these things. So a lot of this is really unpredictable, and that leads you down a certain path. The hyperkernel can observe, adjust, analyze, and adapt to those changes very dynamically. Our goal was to build in intelligence and machine learning into the hyperkernel to automatically and dynamically monitor and optimize performance through this introspection. The hyperkernel can watch its own behavior and figure out the best way to handle each specific activity. This leads us to a model in which we track threads and working set locality. Thank you, Peter Denny. That's again really important. We actually do track working sets. Now, let me talk about multidimensional strategic decision making. Humans find it very difficult to make decisions with multiple factors using different units. Let me give you a simple example. I visit my cousin in Sebastopol. What strategy should I use to return home to Los Gatos? Should I take Highway 880 or Highway 101? It's a real simple question, right? But how do I make that decision? Because there's a lot of different factors. There's a toll versus a no toll alternative. There's a certain difference in the traffic patterns at a given time of day. I have an electric car, so EV charging availability is important to me. I might want to stop and see my son in San Mateo. I might have an arrival time constraint, and so forth and so on. Lots of different factors enter into this decision, and we as humans aren't very good at that. So let me talk about potatoes. Potatoes? What do you mean potatoes? So let me talk about the potato paradox. This is out of Wikipedia. You can look it up. And here's the potato paradox. You start with a bag of 100 pounds of potatoes. And assuming those potatoes have 99% water by weight, you then want to dehydrate it to 98%. And the question is, how much does the bag weigh after dehydration? Well, let me just pause a minute and let you contemplate that. How much does the bag weigh after it goes from 99% water to 98% water? It's not intuitive. We start with 99 pounds of water plus 1 pound of potato matter, and that's where we get the 100 pounds, right? Then we dehydrate it to 98% water. So after dehydration, we still have the same 1 pound of potato matter, but how much water do we have? Well, there's a real simple equation. We have the 1 pound of potato matter. We have 98% of the weight is water. So 1 plus 0.98 equals 0.98x equals x. If you solve for x, you find that it's 50 pounds. By dehydrating 1%, you've halved the weight of the bag of potatoes. I suspect nobody here got that, but if you did, hats off to you. Who would have guessed this? Not me, I got it wrong. Let's talk about what happens during a stall. So first of all, if there's no stalls, there's no overhead. Things run at machine speed. You only get overhead when there's a stall. So our scheduler maps virtual CPUs to physical CPUs, and it's all done, again, behind the scenes. The OS doesn't know anything at all about this. Each stall is caused by an event that cannot be handled by the hardware. The hardware then generates an interrupt, and that's what I mean by a stall. So the hyperkernel then fields that interrupt and has to do something. What does it do? So if the resource is not acceptable, the hyperkernel handles it, analyzes it, and for each stall, there's a constraint-based strategy using nonlinear weighted polynomials. There's not going to be any more math in this talk, by the way, but there's a cost for each of the strategies, S1, S2, and other things. So these are weighted nonlinear polynomials, and we can model these strategies based on the different factors, like, you know, toll road versus no toll road, and so forth and so on. But we can then select the best cost profile that minimizes the costs. So that's what we actually do. So the code for doing these nonlinear weighted polynomials in the hyperkernel, these are all multiplies and adds. It's really pretty straightforward. And then we update the local state as these strategic decisions are made and implemented. By the way, the hyperkernel instances can negotiate with each other. So if I want a page from Len Kleinrock, who's sitting there, if I want a page, I have to ask Len for that page, but Len may say, oh, no, I need that page. I'm not going to give you that page, Ike. So I have to be prepared to then migrate over to the server that Len's page is on. So there's some negotiation that happens over here, and you have to, you know, you have to be prepared for the results of that negotiation. The point is, unlike traditional machine learning, this is a kind of a continuously operating machine learning system with an infinite training stream, and it's self-tuning. So unlike images of cats or whatever, you never know what's going to happen next. So it's continuously training itself and modifying its own behavior. So when a node makes a migration decision, we record what we did and we learn. As a result of uncertainty, we cannot require perfect knowledge of the overall state of the system, because if I start trying to figure out what's going on elsewhere in the system, by the time I figure that out, everything's changed. The state of the world has changed. I have to make all these decisions locally. Now, we have several measures of performance. Here's another simple, I said no more equations, but this is a simple equation. So I have this goodness metric, and I really like this one. It's net guest thread execution time that those are dashes, not minuses. Net guest thread execution time divided by the number of stalls. If the number of stalls is high, then it's not very good. If the number of stalls is low, that's really good. You're performing well. So we need to make these decisions to improve guest thread execution time relative to the number of stalls. To improve performance, accessing the same set of pages should be co-located with each other. So if you have multiple pages in a group, they should be co-located if the threads are accessing them at the same time. And the processors doing that should be co-located with those pages. You can't always do that, but you can try. At the same time, it's probably a bad idea if you have a working set that's working well, i.e. generating a low number of stalls, you don't want to break that up. So there's a couple of different techniques you can use there. And given that, of course, there are exceptions to everything. And I won't go into all of those exceptions. There's too many of them. So how do we treat, you might be saying, well, this is all good for ephemeral stuff. Well, what about I/O, which is often physical stuff? So again, we don't have the opportunity to modify the OS. The guest operating system runs as if all I/O were local on a virtual motherboard, except if you have remote file systems. That's a different story. But it's a distributed system, and we can virtualize the I/O devices and use existing distributed file system techniques, in addition to manipulating page table entries and moving guest pages to nodes containing physical devices. And as I said earlier in the talk, the interconnects today are plenty fast. We started with a 1 gig Ethernet, we moved to 10 gig Ethernet, and some of our customers have standardized on 40 gig Ethernets. And so, that all works, and you don't need the kind of fast interconnects that people were predicting 10 years ago. Now, to treat I/O in a very performant way, we use lots of different techniques, and there's too many things here to go into in detail. We can do remote execution of I/O, we can remote the buffers, we do remote interrupt delivery, we chain I/O operations, we manipulate second level page table entries, we migrate processors, we migrate completed buffers, excuse me. We use asynchronous I/O where possible. We use event-driven I/O, and we defer I/O completion where possible. But here's a problem you may not have thought of. Inside the processor, processors are made from microcode. The microcode actually has a scheduler in there. The host also has a scheduler. What I mean by the host, we build our hyperkernel on top of FreeBSD. FreeBSD has its own scheduler. And of course, TidalScale has a scheduler. And the guest OS, Linux, has a scheduler. And a database might have a scheduler. And if you're running a custom app, the intra-process app might have its own scheduler. So this can get very complicated. The problem is that none of these levels know or can know anything about the other levels. They're hidden from each other. And therefore, they could interfere with another layer very, very easily. And I'm going to give you an example. So assume you have a virtual processor P1, and it's running a guest thread P1 on a node N1, and then it stalls. And during the time of the stall, or perhaps upon completion of the stall, the operating system, i.e., let's use Linux as an example, might decide behind our back to reschedule this thread T1 onto a different processor, P2. But suppose P2 is running on a different node, let's say node 2. The problem we just introduced is this. All the pages that the first thread had been using are on node 1, but now that thread is on node 2. And if that thread continues to use those same pages, the system's going to thrash all over the place, unnecessarily dragging many pages across the interconnect to co-locate the pages needed by P1, now running on P2 on node 2. Fortunately, there's a relatively simple solution to this. And by the way, there's hundreds of these things. When a virtual processor wakes up after a stall and starts running guest code, either OS or application, the virtual processor could immediately check to see that the stack pointer is pointing at a page that is resident on the node on which that virtual processor is running. If so, great. If not, then the OS faked us out and rescheduled us behind our backs. So we might want to immediately migrate the virtual processor back to where the thread had been running before the stall. And in that case, you preserve the working set. So now you might think that you could get by with either page migration or processor migration, but you can't. Both, in fact, are necessary. And let me give you a conceptual reason for that. If all the data cannot fit in one server, one physical server, we of course distribute it among multiple servers. But if we then scan through all that data in all that guest memory, we might have to move a lot of memory around, and this is very slow. But we have these wandering CPUs, and the CPUs move to where the data is, so it's much, much faster. Pretty elegant solution, I think. So here's a couple of performance slides. This is a slide that was from a retail analytics application. And, you know, when you have a single server and you have a certain load on that server, this was running in Amazon EC2, and you exceed the memory that is on that server, you fail. You simply fail. There's not enough memory to run that job. But if you increase the number of servers, let's say double it or even triple it, then it performs very nearly linearly. You've achieved linear performance. This is a standard benchmark TPCH power test. That's the dreaded memory cliff. And we take great pains to deal with that. And I think we do it pretty well. Here's a few other examples. Running R, the programming language R for analytics on Centos fails. This particular application fails at 512 gigabytes. Double it to 1 terabyte and it runs just fine. Adding a few more processors on there, it runs fine too. You've increased the cost unnecessarily, in my opinion, but that works as well. If you take SAP HANA in-memory SQL database, you can also hit a memory cliff. Actually, you can't because SAP HANA won't run if you don't have enough memory, but you get my drift. Increasing the amount of memory to 1 terabyte, the performance is good. And adding more processors, it's also good, but expensive. And maybe you don't need all that expense. Oracle is actually a little better. You can still hit a memory cliff. Running 1.5 terabytes in this benchmark on 2 standard servers, that solves that problem. Running 2 terabytes. Now this is interesting because the 2 terabyte case actually is slower than the 1.5 terabytes. Quad socket is slower, but let's not go there right now because we can't guarantee, you know, the level of overhead. But if you start taking in the number of dollars a customer is spending, in this R case, it's 2x the performance per dollar. In the case of SAP HANA, it's 2 to 5x performance per dollar. In the case for Oracle, it's 10x performance per dollar if you include the cost of the Oracle license. This is a star schema, bare metal, 48 cores, 3/4 of a terabyte using an Intel V5 processor. The execution time you can see here is high. If you look at the number of query sets, you can look at that. But if you decrease the number of cores, but increase the amount of memory, it's 2.5 times faster. And in the paper I published in 2018, there's some explanation of why that is, but that's a kind of interesting result. And if you, with the same amount of memory, same number of processors, but using Oracle's in-memory option, it's 20 times faster. That's, I think, nothing to sneeze at. So queries per dollar, 1x, 5x, 30x queries per dollar. Not bad, I think. Okay, now when I started the company, people would ask me, well, what about the reliability question? You have all these servers. What if one of the servers goes down? Doesn't it bring down the entire system? And I struggled with that question for a couple of years. We are highly compatible. We run a standard set of server hardware acceptance tests. We were running it pretty much every day. We don't run it that way anymore because it always passes. Again, the OS thinks it's running on hardware, and the applications only know the OS on which they're running. So they don't know that they're running on TidalScale. The OS doesn't know that it's running on TidalScale, so the compatibility is pretty high. Software reliability, our software has to be 100%, of course. Hardware reliability is a different matter. Hardware reliability is never 100%. And lately, we've been seeing more and more hardware unreliability as the density of memory increases, and as the amount of memory increases. You're talking now about almost a few atoms to hold a charge. In earlier years, this was troubling, for TidalScale anyway. If one node fails, why wouldn't it bring down the entire software-defined server? And then one day, there was a eureka moment. I was talking with my colleague, David Reed, and it turns out there's a very elegant solution to this problem in which all the servers become hot swappable. This is due to our existing abilities in which we can migrate resources if impending hardware failures are detected through board level telemetry. Now, if you're in a gas-powered car and the oil light comes on, sorry about that. If the oil light comes on, your car doesn't blow up and it doesn't stop. But you should, look into adding more oil or fixing or trying to understand what the problem is. So hardware, it takes a while for hardware to really fail. So here's what we do. Let's say we have a spare in a rack and we detect that one of the nodes is in fact failing. In that case, what do? Well, we can bring the spare and make it active in the cluster. We can then quarantine the failing server. What do we mean by quarantine? What quarantine means is we tell everybody else, don't send it any more virtual processors and don't send it any more active pages. We then tell the failing processor to evict its active pages and evict its active processors onto other nodes. Doesn't matter where, just get rid of them. And so it can do that. And then we can actually power down the server that's failing. And we haven't had to reboot the OS. So we've had a hardware failure. We haven't rebooted the OS. There's the same number of servers now, or if we don't have a spare, we can run it at reduced capacity. But in the end, we have a configuration that is always available. We haven't had to modify the OS. We haven't had to modify the hardware. We haven't had to modify the database. It all runs as before, and we're adhering to published service level agreements. And we can even do rolling upgrades. If you want to upgrade a BIOS, for example, you can use this to do that as well. At the same time, we have thin provisioning. And thin provisioning is interesting because, you might start with, I think I have 7 servers here. When we talk to data center managers and you ask them, well, how many servers does this project really need? They have no idea, absolutely no idea, because their projects ask them, give me the biggest server I can get, always. But we have tools, actually David wrote a very interesting tool recently that measures how much you really need. And so if you only need 3, you only use 3. And then if that starts getting stretched, you can hot add more servers. So, use what you need when you need it. And, if you could do that manually, you can certainly do it automatically. So self-sizing becomes possible as well. So you have these sort of robotic systems which are sizing themselves up and down on an as-needed basis. It's really pretty cool. Okay, now how do you manage all this stuff? So we have this front end. It's a web-based application, actually can run on a laptop, that allows you to allocate resources, configure and manage them, monitor performance and health of the system. This is what it looks like. In this case, there's 20 nodes, 15 of them are used, 5 are free, 354 cores, 13 terabytes, in this case, 4 terabytes of storage. And these are the different software-defined servers. There's an SAP Hana server, TIBCO, Spotfire server, Oracle, et cetera, et cetera. And so these are the available nodes. You hit a button to start up the software-defined server. You can create a server by simply naming it. There's a default set, default operating system, number of cores, number of memory, number of disks. There's a slider here. You adjust the slider to what the size that you want. And that updates the number of cores and amount of memory and disk automatically. And then these are the new settings. You click OK, you start it up, and it's now deployed. It's in the list there, right there. My first TidalScale system. And so what are the possible use cases? Well, you can figure it out, but it's simulation, modeling, graph analysis, retail analytics, business intelligence, data science, financial analytics. We had some bioinformatics, some computational genomics. I'd love to get more customers doing that, but it covers a very, very wide range. So what are the benefits? You have a scalable development environment. If you need more processors or memory, you can just add them. Developers can build, test, and deploy against a performance target. Here's a key point, though. You for the first time, you can now scale your server to your problem. You no longer need to scale your problem to your server. You size the server you need based on the current requirement. You run it on TidalScale, and TidalScale manages the scaling up and down. Your server exactly matches your performance needs. You size the server appropriate to the needs of the app. You pay your software licenses only for what you need when you need it. You save money by using only what you need when you need it, and you can choose on-premise or in the cloud. And so I think it's important to rethink some of these fundamental assumptions we've made, these what's called, Martin Rees calls it counterfactual thinking, how it works. I've explained something about performance and reliability, compatibility, application coverage, how do you manage the landscape, and how to increase deployment options. My friend and mentor, Gordon Bell, says this is the way all servers will be built in the future. There's been the last couple of years, a couple of papers. How do you program an application when memory size is no longer a constraint? That was published in 2017. And Gordon and I co-wrote a paper, Revisiting Scalable Coherent Shared Memory, in the January 2018 issue of IEEE Computer. And with that, I'll take questions. So I'm opening up the chat here.
Oops, sorry, Ike, I was talking. There's a number of questions, and I'll start reading in the chat, and then Leonard Kleiner also, I think you were fourth in a row. So the first question, the problem described on slide 26 with competing schedulers is really interesting. I'm curious to what extent the Linux guest OS's NUMA capabilities helps here. It seems like a virtual process, working sets moving around the physical cluster would be seen as dynamic changes to the NUMA domains, cost coefficients used in the NUMA optimization rules. Any comments on that?
Yeah, great question, Noah. NUMA is really very, very important. It's a strong factor in terms of performance. A lot of the database people who want to control every little thing, they want to specify what those NUMA domains should look like. And you're right that since we are destroying them every millisecond, you can't count on the hardware NUMA domains. And so we've come up with an idea of having virtual NUMA domains. And we can, if a customer wants to use NUMA, they can define what NUMA domain they would like to have, and we will do our best, we'll make best efforts to conform to those NUMA domains. So that was a very hard problem, and I think we have a good solution.
Okay. The next question, how do the hyperkernels of individual machines work together to achieve a global optimum operating condition? Is there overhead of coordination among these hyperkernels? Also, since you're continuously learning, is this a case of distributed learning or local learning by each hyperkernel for its own optimal operation?
Wow, good questions. So we never claim global optimality. We just try to be as good as we can. All decisions are made locally and in conjunction with information that we get, like this negotiation business I talked about earlier. So we keep track of the working sets and we how do I say this? We don't try to be all things to all people. So given that everything can migrate and given that we can move working sets and move processors like the ebb and flow of the tides, you know, we have the ability to, if every hyperkernel instance is doing the best that it can do, there is a possibility that, you know, if we had perfect information across the cluster, we could do better, but it ain't going to happen. So we have to rely on local decision making. And at the same time, there is a very strong motivation to do that because it increases our reliability. So we never assume global information about anything. Every hyperkernel protects itself, protects its own server. And if somebody else asks for something, you know, there's a negotiation and, you know, you haggle. I call it the $100,000 check. So if I ask Shmuel, hey, Shmuel, I need $100,000. Please write me a check for $100,000. Shmuel, as good a friend as he is he's not going to write me a check for $100,000 because he needs that $100,000. And that's okay. So that's a negotiation he and I would have. I may need it a lot, but he may need it more. So so local learning works, and you saw the results.
Okay, so that question was by Aniruddha Gokhale, and the first one was by Noah Watkins. I will merge the following two questions because they're very related. The first comes from David Bader. Are you able to take advantage of heterogeneous processors in a TidalScale system? For example, mixing Intel and AMD hardware nodes and accelerators, e.g. NVIDIA GPU. And then Binoy Ravindran built upon it, asking about taking advantage of Intel servers and emerging ARM-based servers.
Yeah, so we take a hard line on that. We require homogeneous processors. Not only they all have to be Intel, for example, but they have to be running at the same clock rate. Because when you start making these decisions, you don't want to factor in these extraneous things. And of course, the code is compiled for, let's say, x86, and you can't run it on ARM. So we don't even try to tackle that problem. NVIDIA GPUs is something David Reed and I are working on. The answer to that, you'll have to just stay tuned on that one. We have some ideas on that, but we haven't started formulating a good response to that.
Okay, the next question is by Leonard Kleiner. Can you please unmute?
Sure. Hi, Ike. Nice presentation, full of good ideas.
Thank you.
My question is not as direct as these others. You indicated a measure of goodness. You called execution time divided by number of stalls, if I got that correct.
Correct.
And you want to optimize it somehow to increase the goodness. Do you find there's an intuition you get when you think about where the optimum might be? I mean, we found a similar thing when I introduced something called power, and I had a beautiful intuitive interpretation, which you can back up analytically. Is there some intuition, some value you can tell us about for that particular metric of goodness?
The answer is no. And the reason the answer is no is the state space is huge. I cannot predict all the things that might happen, okay? I cannot predict the pattern of data access. I cannot predict, you know, you may write your code so that one day it works really well and the next day you're working in a different data set. The code is fixed, the data is different. So I was a little confused because I'm reading this question in chat about VMware, and I'll get to that in a minute. But you're asking about the goodness metric. All I can do is put constraints on the system so that if the constraints I put on the system are being violated, the system itself will adapt to the new constraints.
You know, one approach might be to take a very clear case, a simple case, whose ratio you can anticipate, a deterministic case, a well-structured case, and then ask, what does your goodness measure give you? And you can say, aha, here's what it's trying to tell me. Sometimes you can suck some intuition out of it.
Yeah, it's all relative, Len. It's all relative. I just know if it's getting better or getting worse. That's all I know. It's beyond my pay grade to do any more than that.
Okay.
No, I'm kind of serious about it. You know, programmers think they control so many things, and they really, really don't. So all I can do is have this, you know, system that dynamically adjusts itself to the changing environment. And, you know, as long as, you know, it's making these local decisions, that's the best we can do. We never claim it's perfect.
Got it. Okay.
Like, we have 3 more questions, and we have hard stop at 7 p.m. I'll go back and forth. First, Hashem, does hyperkernel replace VMware hypervisor, followed by Marcos later?
They're both hypervisors. The VMware hypervisor uses the second level page tables that I mentioned, and we use the second level page tables. So we can't both be using second level page tables. So it doesn't replace the VMware hypervisor. It cannot.
Okay, Marcos, do you want to unmute?
Yep. Sorry, a little bit dark here. Nice talk, Ike. I was wondering about the fault tolerance technique you mentioned when you use telemetry to move over the computation and then the memory away from the problem. Do you have data of how much advanced notice you get and what is the coverage of the failures that you can get using that approach? Like, can you cover 50% of the failures or 99% of the failures?
We can cover the failures that we know about. You know, if you contrast this with what happens today, when a motherboard gets ECC errors and reports it to the operating system or doesn't report it to the operating system, the system just crashes. I mean, that's the alternative. Nobody is handling that telemetry data today. Okay, we have a way of handling that telemetry data.
And how much advance notice you're getting, like a minute or a few seconds?
Oh, it's minutes and hours. I mean, there's plenty of time. There's no problem at all.
Thank you.
And we've prototyped that already. So we know that it works.
Okay, thank you, Marcos, and everybody else. Next question, worth $100,000 regarding reliability. Is the replacement physical server in active-active mode, active-passive? What is the standby definition? What about catastrophic hardware failure not captured via telemetrics? For example, yank the power cable to a server.
Oh, well, come on, you know the answer to that. Well, first of all, these things are in protected data centers and they have, you know, uninterruptible power supplies. So it really, you know, yeah, you can, you know, somebody might trip over a power cord and yank it out, but, you know, it's not something we're going to design software to fix. And it just doesn't happen. As far as passivity goes, the large data centers have large numbers of servers sitting there not doing anything. And so while we like to keep them local, even if you didn't have a hot standby, while you fix the server or you replaced an ECC DIMM, you know, the system continues to run. It just runs maybe a little slower. It's not that big a deal.
Okay, I think we exhausted all the questions, but I have 2. I liked your notion that you're not trying to be all things to all people or all applications. So I was curious, for which applications is TidalScale suited and for which it is not?
Oh, that's a very good question, actually. Most of the marketing opportunities we're going after is these large memory requirements for these in-memory SQL databases. And the reason for that is there's a lot of instances out there where people are running Oracle in this fashion or SAP HANA in this fashion. They're easy to identify and we're getting good results. There are very few examples that I've seen where it doesn't work well. I'll tell you one of them, and that was a computational genomics example a few years ago, in which there was a large table that was being rehashed every cycle, and that rehashing was destroying locality every time you went through that whole cycle. And so once we realized that was going on, I wrote a nice letter to the customer. I said, look, I don't think this is the right solution for you. The customer got the letter, recoded the solution, and wanted us to run it again. So if the software is actively trying to defeat our ability to form the working sets, we're going to have a problem. No question about it. Was there another part to that question?
Well, I do have another part that you just motivated. I had another question altogether. So GUPS-like workloads will not be well suited where you are chasing the pointers around the whole distributed space. Is that correct?
Well, no, we do graph applications all the time. As long as there's a way, and we don't have to predefine what that pattern is, but as long as the hyperkernel can form a working set, we're good to go. Okay. If it's totally random, which is kind of rare actually, then there's going to be a problem.
Yeah, I think that's what GUPS is. But anyways, you already partially answered my second question, and that was the best way to define a company is by defining who its competitors are. So can you still repeat that, even though you mentioned?
Yeah, well, for years, we only had one real competitor. That's a company that was in business for quite some time, and they went out of business. So I think we're the only ones doing this now.
Mm-hmm. Okay, well, it's 7 p.m. I highly appreciate it. It was exceptional talk, and thanks for great questions, everyone. I hope to see you again next month. Bye, everyone.
Okay, take care.